Okay, so RIP my inbox this morning because I got about 1 million emails saying, hey, can I have an extension for various reasons. Here's the deal with, so obviously this homework assignment, like a lot of times for many people, required a lot of like last minute debugging, or at least end of project debugging. Don't be surprised if that happens in the rest of your careers, as far as like you think you have a problem and then you spend 80% of the time debugging like 1 or 2 little things. That's the way it goes. I understand debugging is hard, so don't get me wrong there. But again, I will say it many times. Many of the emails were, oh, I didn't get to start it until late. And I'm like, didn't I tell you that it's probably a good idea to start a little early? I get it though. If you're still like worried about it, then email me. That's the first thing. Second thing is it true that tough students in general, correct me if I'm wrong, tough students in general are perfectionists? Is this like a true statement? Because a lot of times, I love the fact that you guys want to get every test passed. I think that's awesome. But if you don't, you can't stress too much about it, right? If you miss like 10% of the tests, you still get like a 90% on the homework, right? So it's not the end of the world not getting every test correct. So those are my comments on homework 4. We will try to start grading them probably tomorrow night or Wednesday. Yes?
I don't know if this goes for other people as well, but I thought it was a requirement for submitting the actual assignment that you pass the test.
It doesn't no, it does not have to pass all the tests to be submitted. I mean, it can't have errors, like you can't have compile errors, because that will fail the provide. But otherwise, no, as long as it says, you know, as long as it gets to the point where it says these tests passed or failed, then it's submitted. So that, yeah, sorry about that. David?
I would recommend to facilitate people feeling okay about submitting
Yeah.
failed tests. Maybe instead of saying, these are the tests you failed, say, hey, you passed these 20 tests.
Yeah, you know, that's, you're a glass half full kind of guy, right? You like that instead of the other? Yeah, that's sure. I could update it.
I think for most people, like, you get this flashing message like, you failed here, here, and here.
Yeah. I mean, we did test like 30-something times. Yeah, there were a lot of programs, yeah. And I know that's kind of a bummer sometimes too. But yeah, that's fair comment. I will take that as a fair comment. Let's see, homework 5 is going to be, actually homework 5 is going to be a little bit different. It's going to be on sorting, which is, I gave this assignment last year and people really liked it. What it is we haven't talked about sorting yet. We'll do that on Wednesday, and that's when I think the assignment will be up. But what it is you guys will be responsible for writing 3 different types of sorts, and we will talk about lots of different types of sorts. You'll be responsible for writing 3. 2 of them you have to choose from a list of like these ones you want to implement. The third one you get to implement completely on your own. If you want to create your own sorting algorithm, go for it. If you want to use some wacky one that you read about on the internet, pancake sort or some weird sort, you could do that. So there's lots you can't do bubble sort, no. But yeah, bogus sort. You probably don't want to do that one. But anyway, we'll talk about those details. But anyway, that's going to be probably starting Wednesday. It'll be about the 2 weeks as well. We're down to like 2 more assignments, I think, for the semester, I believe. Kind of crazy. Yeah. They get a little bit longer. The last one's especially long. OK, any questions before we get going on homeworks? All right. Today, we're going to talk a little bit about this thing called the public HTML folder, which you have all typed in at some point because that's where I keep all the stuff for our website and labs and things. Then we will talk about Lab 7, which actually uses a web front end and a back end, which you guys create. So that's kind of neat. I'll talk about that in a minute. And then we'll talk about a really cool data structure called a heap, which we kind of previewed the other day in terms of priority queues. OK? All right. So the public HTML folder. You may or may not know this, but you have, or at least should have, a public HTML, public_HTML folder in your home directory on the homework server, or rather any of the tough servers. If you have a CS account, you've got a public HTML folder, or at least you should. And I'll go into the lab tonight to make sure it works out to get everybody up to speed on that. But that means that you have a space for a website. If you want to do your own website, you can put it there. Okay, your website is www.cs.tufts.edu/tilde, your CS username, and that's it. Now, if you went there right now, it would probably say either file not found or some other error message because you don't have anything in that folder. But you can put something in there. If you wanted to publish a really simple website, put a file called index.html into that folder, set the proper permissions, which I'll talk about in a second, and you will have a website of your very own. Okay? And you should definitely play around with that. What I mean by permissions is, in order to run a file on a Unix or Linux-based system, you have to set permissions so that some people can read it and some people can't, and so forth. If you're a public HTML website, you need to set it so that everybody can read that file. So you use this file called chmod, right, which means change mode, which basically means change the file so that everybody can read it in this case. A plus R means all people can read it. And then you'll be able to do that. If you have folders, individual folders inside your HTML or inside your public HTML file, everybody needs to have what's called executable privilege, which means they can actually go into the folder and run programs from in there and read other programs as well. So it turns out that's the way it works. And you would do that by saying chmod everybody plus, meaning change to reading and executing. And that's how you would do that. Okay, so it's kind of cool. You can actually have your own web pages. Tonight's lab will create a web page for you in a folder called Lab 7. So unless you have a folder called Lab 7 already, you don't need to worry about it overwriting anything else you have in there. But that's what it's going to do in the lab. Your web pages can actually use programs written by you on what we call the back end, which means the web page itself is like the front end, and then on the server there's programs that you can run. I believe you guys are actually limited to running maybe Perl and maybe PHP. I don't think you can run some of the other, like Python or some of the other back end things. We have to do a little kludge where we make it so that you run a Perl file that runs the C++ file and so forth, but it works out all right. You can certainly check it out and see how we do that in your folder. Normally, the back-end languages are these languages called PHP. I don't like it so much. Perl, which is pretty good. Python, which I happen to be a fan of. Other people in the class are not. And Ruby, some other back-end sort of programs. Rarely do you use C++, although it's generally a pretty fast language, so you can. The one thing you have to remember, and this is when you get to the lab tonight, you have to make your file on the server before you can run it through the web page. And people always forget that and wonder why their program's not working. But that's that. Okay? Let's see what else. The lab tonight is about tries. And remember the try thing I showed you on the web page? That's what you're interfacing with. You're going to interface directly with the try front end for that. So that's that. And let's see what else. So we're not really talking about web programming in this class. If you want, there's a class called Comp 20, which is really popular. Everybody wants to take it, and it's always so popular. And they had to not let people in this year, so get in early if you want to take it. That will teach you how to work with HTML, back-end languages, and figure out how to do web programming in general. Okay, it's kind of fun. I mean, it's fun to be able to do that sort of stuff if you want to interface with the world as it is. Okay, questions on programming for the public HTML folder? You'll get to practice it tonight. Okay. No other questions about that? Okay. All right. So what are we going to do today? We started last week with this idea of a priority queue. Now remember, a priority queue is the data itself is separate from the actual priority of that data. And we had lots of examples in the real life, right? And we decided to draft a couple of priority queues using an unordered list and an ordered list. And this was what the asymptotic behavior was for it. Not the best in the world. Not too terrible, but whenever you're talking about linear asymptotic behavior, you hope you can do better. You can't always for various things, but you hope you can do a little better, especially for something as easy as give me the minimum value, right? And that's about it. So we have to talk about a better data structure than the lists. Okay? That's where these heaps come into play. Okay? Heaps are the following. It's a data structure. You can use it to build a priority queue. A lot of times they're actually used interchangeably, right? A lot of times you get So you'll say, hey, it's a heap when you mean a priority queue. It's just they're that much interlinked because of the fact that they're very good for priority queues. It is a tree-based structure that follows the following one property. Parents have a higher priority than their children. Okay, that's it. Parents have a higher priority than both of their children. No more of this like left is less and right is greater. It's now just if you're the parent, you've got a higher priority. Whatever that means, it can be either less or more depending on how you describe priority. Okay? Here are two heaps. One is a min heap, where the minimum number is higher priority, and max heap, where the higher the number is the priority. There's the better priority. Okay? Notice, take a look at these for a second. These always look a little weird the first time you see them, because you're used to thinking binary search trees, yet these aren't binary search trees. They have one property, and the property is everything below you is lower priority. Everything above you is higher priority. That's the only thing that matters. Right? So take the min heap for a second. 10 and 8 could be swapped, and this would still be a legitimate heap. Okay? It doesn't actually, the order on the left and right matters. Is there a way to traverse a min heap and get out the exact order, like the numerical order of priorities? I guess the first question is, can you do that with a binary search tree? Yeah, remember how you do it, Natasha? It's not pre-order, you're close. It's actually in order, because it's in order, right? So you're doing it in order, and you do it in order, and you can do it. Can you do it with a binary search, or for the binary heap?
Do you have to have them in the same order that you traverse?
Do you have to have them in the same order first? What you need to do is you need to do 5, 8, 10, 11, 12, 13, 14, 22, 43.
But you need to traverse in that.
You don't need to, you can traverse them however you want, but there's no traversal that's easy to do this way, right? Because the 5 and the 8, you'd have to go this way and then back up and go this way, but then go this way and then back and go this way, but then go all the way over to here. So there's no real traversal. This is not there's no defined like left and right order at all for a binary heap. Okay? There's no implied orderings from the siblings. Right? With a binary tree, we knew all the siblings on one side were less than all the siblings on the other side. That was definition. Heap, don't know that anymore. All we know is that the parent has a higher priority than its children. So both of these are heaps. Okay? That's the way it works. What's nice about this is it actually simplifies some other things a little bit later. Okay? All right. Heaps are what we call completely filled. Okay? In other words, somebody has asked this in the earlier class. They said, hey, do you need to do like an AVL property on a heap? Like, keep it balanced. No, because you can't unbalance a heap. Remember what a complete binary tree was. Every level is filled until you get to the last level where you fill left to right, until you run out of things to fill. Okay? So in this case, you can't have a node over here before you put one here. That's what it means. Okay? All right. So basically, you have the maximum number of nodes is out to, in this case, out to here. And internal nodes, right, the internal ones are to the left of the external ones, which are the ones that are just node, empty. Okay? All right. So that's the idea of a heap. Why do we do this? We'll see why in a second. Like, why do we make it a complete binary tree? You'll see in a second. OK, here's what I want you to do. I want you to think, talk to your partner, talk to your neighbor, whatever. How might we store a heap? What do I mean by that? I mean, in memory, what's the best way to store these values so that we can actually access them? Think about that for about 5 or 6 minutes. Okay, talk to your neighbors about this. What are you guys thinking?
Just throwing around some ideas.
Like what?
Well, that we can't, because in the same way in binary search tree, you could traverse it by knowing that, like, the left is greater, the right is greater. You don't have that here. So,
True. But traversing it's a little trickier. It's different.
would you just do it based off of priority, and then like you go left or right? It doesn't
Yeah.
really matter.
Yeah. Yeah. Let's think about. So you could do it in terms of the. You could do it in just terms of the root has a left and a right, just like a binary tree, right? But maybe there's a different way to access the data. I'm not necessarily thinking you'll figure it out. Let's just kind of. What other ways do we have for storing data?
Linked lists.
Linked lists, okay. Okay. Can we think of a way to do either one of those in a binary tree? Linked list is tough because it's just got one file on, right? But what about an array?
Like abstract data types, or like we were talking about
Data structure, like how do you, yeah, if you wanted to stick this into an array, how would you do it? Think about it. It's okay, that's okay. Just think about it for a second. I think you're getting there. John, how you doing? What are you thinking? Okay, all right. All right. You guys think you got it figured out?
Yeah, we can
Okay.
figure it out, right?
No idea? That's all right. That's all right. How are you guys doing? You figure anything out?
We're thinking about arrays of arrays.
How would you do it in an array? Oh, arrays of arrays? Is that what you said?
Yeah.
Okay. How would you do that?
Because well, first we have one array for the levels.
Oh, for the levels. Okay.
Then you can, I guess, store the size of each of the element in the first element, and then put all the data after that.
Okay. Okay. That's not a bad idea. I like that. I like that idea. Okay. We'll get there. We'll see. You have some more ideas? Like what?
We went to power looking for your representation, but then we were going to say like 2 element arrays.
Oh, I see. Instead of a, okay. That's not a bad idea. It's not a bad idea at all, actually. Instead of like instead of a node. Yeah. Okay. Okay. All right. I heard some good ideas. Who has an idea about how we might store a heap that makes sense? Ethan.
Well, we thought it might be good to do it in a dynamic array with the things oriented as if you read it from like left to right.
So a dynamic array.
5, 10, 8, 12, 11, 14.
Oh, I see. 5, 10, 8, 12, 11, 14, 13, like this, you mean?
Yeah, because you always, like, because it goes up on the left side first, that will always actually indicate the structure.
I think I had 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Off by 1.
You have to erase the full thing.
Yeah. All right. So you're saying put them in the array this way, like put what where?
So 5 would go first.
5,
10,
10,
8,
8,
12,
12, 11,
14,
14, 13,
22,
22,
43.
43. Okay, that's an idea. That's an idea. What's good about this idea?
Well, for one, they're all pretty close together, so you can access them without having to like jump all
They're
around.
all pretty close together. Okay. Well, we'll go on to that. Who has a different idea? No. Yeah, Josh. The lower, yeah, well, I think that's what the lower the index, the higher priority, kind of. No, not really. Oh, you're saying like actually sorted.
Yeah, well, as in because you have the higher levels farther to the left, so
Yeah.
you know that you're going to have a higher priority.
The higher levels farther to the left? What do you mean?
Well,
Because this whole thing could be reversed 100%, right? It could be completely flipped. It could go 5, 10, and 8 could be over here, right? And it's still a heap. Okay?
yeah, I'm just saying, even if you switch things within the level, you still know, for example, like element 0 is going to be a higher priority than element 1 and
Oh yeah, yeah, sure. You definitely know that. Yep. But is that going to be different than their idea?
Well, I was just trying to say that that's good about their idea.
Oh, okay, okay. I see. It's good about their idea. Okay, good, good. All right. Other ideas? Yeah. Whoops, sorry. Yeah, and then back. Yeah. First here. Go ahead. Yeah, you. What's your name? Tyler. Yeah.
What about an array of pointers to other arrays?
An array of pointers to other arrays.
Pointer to a one array, one second, two pointer to
So this array, what's in this array?
the first effect is a pointer to an array of like one.
An array of like one like this? Okay.
And the second one's a pointer to an array of two.
Oh. Like two? Okay, and this one's like four. Oh, four. Interesting. Okay, so, oh, I see. So then you're, oh, I get it. Okay, that's interesting. So what would you put in? So you'd put, this would be a 5, and this would be 10 and 8. And then, what would this one be? 12, 11, 14, 13? Okay, that's interesting. That's kind of cool. I mean, I guess what's the, well, so how would you figure out 5's children? The next pointer. Okay, how would you figure out 8's children? It's the next pointer, last two of the next pointer. Okay, this sounds like a good idea. I'm thinking it might be a little bit more intense than what we want to do, but I like the idea. Yeah, what did you have?
You can make a struct for like a number, and then instead of having like right and left pointers that point to the nodes, you had right and left things that pointed to like the indices on the array.
So you could have a struct that points to indices on an array. So you still have an array?
Yeah, you still have the array, but the array, the order that the numbers are in the array doesn't matter.
The order that the order is completely. Oh, so you're saying the struct is going to like point to the correct places in it.
Yeah, so like you have like
Okay.
the top of the heap, and then you can go
Okay.
left and right.
Okay, I see what that means. Okay, so you can modify those easier. Not a bad idea, Max.
You replicate a tree using nested 2D arrays.
You could certainly replicate a tree structure, and you're saying each structure is a two-dimensional, each node has an array of 2.
Yeah.
Okay.
Except it's just that is the node.
All right. That is the node, and inside it's an array of 2,
Yeah.
and then inside each
Pointers.
pointers to the other. Okay, so it's very similar to a regular binary search tree. Okay, good, David.
I guess, I mean, I know we haven't really spoken about what it's going to look like when we do things like insertions or anything yet. But, I mean, linked lists is always going to be a consideration.
Yeah, I guess so. You could just link this one to this one to this one to this one. Yeah, that's not a bad idea. Given what I've said before about the use of linked lists, and you're probably not going to see that, but that's a good idea. It's very similar to this array concept. Okay, good. I like all. Yeah, Sophia.
Could you do a linked list where every node has an array for each level in it?
A linked list where every node has an array. That's pretty much what we were saying back here, right?
Yeah.
Every node has a linked list for another array. What's in each array?
The things for each level.
The things for each level. Okay. A lot of you guys are thinking level by level. That's interesting that you're thinking that way. Okay. Turns out that the first one was actually the one that we'll look at. Okay, I like this way. And this way is good for another reason. It's very simple, isn't it? Okay? With the null nodes, how many total values could there be in this heap? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Which is what number? Yeah, I like that. 2 to the 3 minus 1, or 2 to the n, total minus 1, right? Levels minus, well, levels plus 1, I guess. Minus 1, which is actually kind of nice. And then, in fact, you'll notice I drew 16 of them here, because there's, like, 16 is a nice number, because it's 2 to the third. It's actually kind of a nice computer science-y number. Powers of 2. Okay. Here's a question for you. I like what we've done here. If this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15, okay? Can you, using just math based on the indexes, tell me what the parent of this one is? No, not the parent, the children, rather. The children of 5. What is it? what are the children of 5 in this case are 10 and 8. Yeah, let's say it's going to be, let's say the index is going to be I. So it's going to be for the parent of, or for the child of, the left child of 5, it's going to be 2 to the I.
Wait, whoa, what?
Let's try a different one.
Okay.
Let's try the parents, or the children of 8. The children of 8 are which children are 8? 14 and 13. So to go from index of 2 to index of 5 or index of 6, how do we do that mathematically? 2 to the I plus 1 gives you the left child. 2 to the I plus 2 gives you the right child.
Wait, are you saying 2 to the I or 2
I mean, sorry, 2 times I. Thank you. 2 times I plus 1 and 2 times I plus 2. In this case, it's the same, but you're right. 2 times I plus 1 and 2 times I plus 1, 2. And how do you find the children of, or the, sorry, I get it backwards again. How do you find the parent of a node? Divide by 2, but it gets a little wacky. How about we do this? Nope. We still have only 2 to the n minus 1. So aren't we wasting one up there? Like, because it's 2 to the n minus 1 in this case. Let's waste it down here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Did I miss one? Yeah, there we go. I think I must have missed one. Wait. 1, 2, 3. Yeah, OK. Now, forget about this 2i plus 1 and 2i plus 2. How do we find the parent, or the children of 8 now? We need to go from 3 to 6 and 3 to 7. 2i for the left child. And then 2i what? Plus 1 for the right child. And how do you go backwards to from the child to the parent? Yeah, for the parent of index 6 is index 3. 2 divided by I. What's the child of, or the parent of 13? Also 3, which is, did I say 2 divided by I? I meant I divided by 2. Thank you. You guys got to keep me honest. It's what kind of function is this? Integer division function, or? Yeah, you can do all that. I like to call it the floor method. OK, what it means is integer division and basically round down. Right? OK, so the parent of 14 at index 6 is 6 divided by 2 gives you 3. What's 7 divided by 2 in integer math? Also 3. It's 3.5, but you just round down. That's what this floor thing means. So this gives you the parent. Now, why do I care about this? How easy is it to find your children and your parents using one arithmetic expression, right? You either multiply by 2 or multiply by 2 and add 1, or you divide by 2 and do an integer divide, which is easy for a computer. Okay? That is a pretty good way to do it. Okay? The reason we can do this is because we enforce the fact that it's a complete binary tree. Right? The fact that we know that 12 has children at 22 and 43, if we look at 12 in here, 12 is index 4. Well, we know that its children, based on this complete binary tree, has to be 4 times 2 is 8, 22, or 4 times 2 plus 8, or 4 times 2 plus 1, not 43. So that's how you know that these two are the children of 3. This will become very, very important once you actually go and code these things. Okay? Questions on that? Here, I'll put the diagram up there. Okay? So good job. All you guys who thought of arrays, good job. Okay? The reason we put it at 1 instead of 0, 2 reasons. First reason is the math is just a little easier, right? Second reason, we've got we're going to have a power of 2 generally number of nodes. we might as well just use the one at the end, or do like have this one be the overflow. And by the way, if you're swapping things, you can always use this position to swap things if you want. Not a bad idea to do that either. Okay? Questions on representation of this? Okay. All right, so here's the math again. It's on the slides if you want. The heap size is the number of elements actually in the heap, not the total array size. Right? So in this case, it's going to be 1, 3, 4, 5, 6, 7, 8, 9. In this case, it's 9 elements in the heap. That's the heap size. Okay? All right. So that's how we do this. Now, go back to priority queues for a minute. Remember, 3 relatively simple operations. 2 are kind of duplicates. Right? We can do min element, get the minimum one. We can do insert item, which means put it in the heap. And we can do remove min, which means boop, get it out of the heap. When you do these 3, you need to, just like with binary search trees and AVL trees, you need to keep the heap property. Okay, so when we do these. We could do a max element and remove max for a max tree. Okay, but you need to keep the heap properties. Okay? How easy is it to do min heap or min element? Where is the min element in our definition of the array? It's always the first one. It's not 0. It is the first. It's heap 1. So the min element is always just heap 1. What's the asymptotic complexity of that? Constant. Woohoo! Okay, we love constant. Okay, so getting a minimum from a heap is easy because we know the minimum is always the top element. We know nothing else about the other elements, right? Except that they're lower. But we don't know which one of these is the min off the top of the, like just off the bat. But we know this one is the min by definition. Okay, nice. All right, I'm going to make you think about this one again. How do we go about inserting into a binary heap? So for instance, in this heap, let's insert 9. I want you guys to think about how we're going to do it, and then what operations we might need to do to keep the heap a heap. Okay, think about that for 5 minutes or 10 minutes.
Where 9 is the key and all the other things are keys?
Yeah, 9 is the key. All the other ones are keys.
Oh, thank God.
What?
Nothing.
Okay. Hey there. I haven't seen you around much. Caroline, nice to see you. What lab are you in? I must be in the 4:30 Wednesday, or no?
Tomorrow.
4:30? Oh, 3. Okay, good. How's the class going so far?
It's all right. It's going well.
Good. Okay. This project turned out all right for?
Yeah, I really liked it.
Okay. Good. Cool. Good. What do you think of this?
Of the heaps?
Yeah, what do you think of like inserting? What do you think we have to do? Where could we put it? Okay. It's probably where it has to end up eventually.
Yeah.
Or where 8 is, I suppose, right?
Yeah.
But you got to move 8 somewhere, so maybe it's got to be below it, yeah.
Yeah.
Where's the next position in the heap that has to be filled?
The one to the right of it.
Yeah. What if we threw it there? Yeah. That would break the heap, right?
Yeah.
But then how might you check and see the next, like what's the next step? If you're going to, okay, now the heap's broken, what do we do with 9? Where does it need to go?
You would swap it with the next one.
Okay, so take a look at the next one up. That's its parent. Would you swap it in this case?
Yes, and then the heaps.
Okay, what's next?
And then you swap it with the parent.
Ah, okay. Would that work every time? I bet it would. Good job. Yep. Hey, did you figure that out? Working on it still? Yeah, the program. Okay. All right. More time. How are you guys doing? What are you thinking?
We're thinking about whatever element it is, you insert it in the correct spot. And
Okay. The correct spot being the next available.
Right, the next
Okay. Good.
available. And then you basically check with the parent to see if it's smaller, and you swap it as needed, and basically go up the tree and swap.
That's a good idea. I think that's a very good idea. Good. What do you think? Uh-huh. I like it. Good. Yeah.
Probably need to store the height of the tree.
Think so? You need to store the max element. That's about all you get. You don't really get the height. Does the height matter?
Well, because you want to make sure that you never have a node that's at too, like you don't want to leave it too deeper than another, right?
True. But we know the size of the heap, right? Like we know the max, the size, the heap size. So you know that the heap size in this case is, what did we say it was, 9? 9. We know that's how many are in there. Sure, I'll give you that. You get to know the heap size. So where's the next place one could go?
Well, not. You were saying that there are 3 places in this tree, right? You could go under either node of either set of 8, or you could go 10.
Okay.
It goes where 10 is.
But let me ask you one more time. Where's the next one that's going to get filled in this tree?
11's left.
Okay. What if we threw it there first? What if we put it there? And then what? It would not be a heap anymore, correct? And then what could you start doing?
You keep checking its parents
Ah.
until and then you.
There you go. I like that. Okay. All right. I heard lots of good answers. In fact, I heard about 4 or 5 correct answers, which is awesome. Okay. Let's see. I'm forgetting your name in the green back there. Sorry. Zach, was it? No. Yeah. Zach. What did you say, Zach?
I said put it in the last or the heap size, so basically the left child 11.
One sec. Zach says put it here. Why is he saying put it here? I heard it back here. Who said it? Next spot. Isn't this one going to be a node after we're done here? You know it is, right? You know there's going to be a node there. So you might as well start out sticking one right there. Okay, keep going, Zach.
And then you're going to check if it's less than the parent. And then
Check if it's less than the parent. And if it is, they're gonna swap. And then what?
and then just keep doing that until
Up until the top. Not bad. Okay. Let's demonstrate this. We've got them all here, right? Okay. If you go to the where am I going here? Heap visualization. It's the one we've used before. Is this the one? Yeah, this is it. I hope this is the one. Okay, so here's what I'm going to do. I'm going to insert this so we can see it. So let's see, 5, 10, 8, 12, 11, 14, 13, 22, 43. Okay, so, and now I'm going to slow this down again. Okay, so the next thing we're going to insert is 9. And what Zach and some other people have said was, look, it's got to go here. So you might as well put it there first, because it's going to be the next one in the array. Because we're not going to put it out here in the array, because that doesn't make sense for our heap. We want the heap to be as far in the left in the array as possible. So it's going to go right there. And then we're going to just check with the parent. How hard is it to find your parent? Divide by 2. All right, it's easy. Right? In fact, computer scientists love division by 2 because you can actually do what we call a shift of the bits, which means that you've got, you know how numbers are made out of binary digits, like there's ones and zeros, that can make up all numbers. If you take a number and you chop off the last digit, you've divided it by 2. Right? And you chop off the next digit, you divide it by 2. That's how easy it is to divide by 2 in binary math. Anyway, it's real easy. OK, so it's going to go right here, and then check, check, check. And the two swaps are going to be there and not the last one. OK, let's see what happens. It's going to go in. It's going to check. It's going to swap. It's going to check. It's going to swap. It's going to check. And it's not going to swap. OK, pretty easy to do. Anybody want me to do any others on this one? What ones do you want me to do?
42.
I'm going to insert 42. Where's 42 going to go? Next available spot. The next available spot's right here. So 42 is going to go there. And then are we going to do any swapping? No swapping. Right? 42 goes right in there. Check. No swapping necessary. John?
So it's OK that 11 is less than 12?
Sure. Why would it matter that 11 is less than 12? The levels, even though you guys focused on the levels don't matter. The heap property is your parents are all higher priority than you. Kind of like real life, right? Like, I mean, like who gets to eat first at dinner, right? Your grandparents or whatever, right? I mean, right? OK, well, what else? Where's the next one going to go? OK, what if I inserted a priority of 1? The guy with the knife in his neck going to the hospital, right? He goes in where? He goes in here, and then he goes swap, 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 and all of a sudden he gets seen next, and hopefully he gets saved. Right? Down there, swap, swap, and swap. And there we go. And the min element is now 1, and he gets taken off the heap, and blah, blah, blah. Questions on this? Pretty straightforward, right? Like not a hard concept. Not too bad once you think about it, OK? Here's the actual algorithm. That moving up thing, it's kind of like a bubble going bloop, 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 right? So we call it a bubble up. Or we call it an up heap if you don't want to be fun, right? We call it a bubble up. That's the bubbling up, meaning you start in one place and you go bloop, 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 and bubble it up to wherever it needs to stop at. OK? Compare the element to its parent. If it's in the correct order already, you're done. You don't need to do any other searching. If not, you swap and repeat step 2. Swap them and then go back up to the next level and do it there. OK? Asymptotic complexity. Worst case is logarithmic, right? Right? Let's see. This is the one. 9, 9, 9, 9, 9. There we go. Worst case is logarithmic. Average case turns out constant. Oh, which is very nice. OK? It turns out that because of the way the heap is drawn, the average case is actually constant, right? And I'm not going to prove that to you, but you can go read a paper about it if you want. If you happen to be on, listen to you. If you happen to be on the campus, you'll be able to get that directly. If you're a member of the IEEE, you can get it, or just you can probably Google it and find out anyway. But this will prove to you that the average complexity inserting into a heap is constant. That's awesome, right? It's exactly what we want. Okay, very nice. Okay, so that's how we do insert. Okay. All right. How about remove min? Now, which one needs to go away? The 5. You tell me how getting rid of the 5 and rearranging the heap is going to work. Go. Try it. We'll talk amongst yourselves on this one. walk past you in here? I just want to walk over here for a second. Yeah, thanks. Cool. What do you guys think?
We're trying to decide.
Okay.
We're trying to figure it out on here first, and then translate it to the array. Yeah.
Okay. So what's the first? What's the first? What are you thinking first? 5 needs to go away, right?
Yeah.
Whoop, gone. Then what?
We find the minimum child.
Yeah, you know, a lot of people think that. But doesn't that mean you're going to eventually have to go through the whole tree?
Yeah.
Which would be what kind of complexity? And you don't really want to do that if we can help it, right? So I like the way you're thinking, but if 5 is gone, what's the next element that goes away? When this is done, which element is missing from the heap? In other words, take 5 away, we're going to have to rearrange everything. There's going to be one fewer element. Which one's it going to be? Well, that one's, you're going to have to rearrange so it still looks like a heap. The 13's going to be gone. So what might you do with that 13? You just got rid of 5. That is what I like. Think about that a little bit more. Okay. What are you guys thinking?
We're thinking kind of like a bubble down.
Oh, bubble down. Okay, what's going to bubble down?
So think of like the last one.
Yeah.
3, 5, 6.
Yeah. Oh, I like that.
Then we have to like compare now the children.
Sure.
Yeah, then probably down to 8.
Yeah.
Then we compare again.
Good.
I think we're saying like the level of
Usually the one which is higher priority.
It's the lower one.
Yeah, the lower one.
Yeah. Perfect.
Yeah, then actually
Good. Awesome. I like it. What are you guys thinking?
We're sort of talking about how do we know if the only invariant is that's the right word, right?
Yeah. Yeah, that's the invariant. Yep.
How do we know which of its children has a higher priority?
Well, you can compare them.
Oh, and then
Right.
9 would just have a higher.
9, in this case, 8 would have a higher priority. Yep. Yep. Yeah, okay.
And then you'd probably compare its children again and then move it up again.
The problem that would work. The problem is you're going to have to do basically you're going to have to do a lot of comparing in there and moving and like for instance, if we compare the 8 and the 9, how do you know that the 8 goes up there? Because what if there was something farther? Well, let's see. Could it be the case that? Let's see. Could it be the case that? Well, I guess what happens in the? What happened? I guess that would probably work.
Could you just?
That would probably work.
I think maybe just because it's an array, could you just switch, or like remove 5 and replace it with its like least priority child, and then just really move everything down?
You could do that. That might not. Let's see. Would that work? That should work. Although there might be a case where something on the other side is less still than or other priority. So I don't think that would work in every case. But there's one value which is going to be gone at the end of this. Okay. So you're getting rid of 5. So now you've got a place to put something. You know 13 is going to be gone. What can you do with that 13? Put it at the top. And then what?
Compare it with 9.
And then what?
And then keep going
And then
down.
keep going down. Well, what might we call that?
Bubble down.
There you go. I like it. I like it. Okay. Once again, I heard some really great answers. I heard some crazy ones too, but I heard some really great answers as well. Okay, let's see. Erica, we chatted. What did you think we were going to do? Not Erica, Julia, we chatted. What did you think we were going to do? Sorry, Erica, I didn't chat with you. Now, what do you think now? Yeah. You got there eventually. Okay, pause for 1 sec. Remember how last time Zach said, hey, add the one at the bottom. And Julia is now saying, take away the one at the bottom. Why is she saying take away the one at the bottom? Alice? Because you know this one's going to be gone by the end, right? So you might as well put it now. Where are you going to put this one? Yeah, isn't this one going to be gone? That's the one we're removing. So you could actually go, 5's gone. We've got a place for it. Put 13 there, and then what? And then you bubble down, right? Which is a little bit trickier as it turns out, because you need to compare to both children if they exist, but which one do you replace it with? Does it matter? Let's see, 13 goes here. Well, we can't, this has to be smaller than both of its children. So if we replaced it with 9, we couldn't do it, right? So we have to replace it with the smaller child, and then you just bubble it down. Okay, and it's exactly the opposite of before in that sense. So here's the actual algorithm, right? We knew removing the root, so we retain a complete tree, replace the root with the last element, which works, one set. And then you bubble down or down heap if you're not fun. And you compare the root with its children, right? If it's in the correct order, stop, we're done. Otherwise, swap with the smallest child and repeat step 2. In other words, down the tree. Okay, or the heap in this case. You do have to be careful to check if the children exist. Next week's lab is on heaps, and you got to remember to do that. Check if the children exist. If the right child exists, guess what? Well, no, the left child has to exist, right? Because how can you have a right child and not a left child in this? You can't, right? You couldn't have this one. You couldn't have this one and not this one, and you couldn't have this one but not this one. Does that make sense? Yeah, I think I said that the same way. You can have this one without having this one, but you can't have this one without having this one. It's impossible in this structure, right? That's what I meant, but I didn't say it. Okay, so you had a question back here, yeah.
Why is they like
So,
go down to the other end, like the end of the other end?
if we go to the end, you mean down here?
Let's say the each was like 50.
Let's say this was 50.
Yeah.
Okay, it goes up here.
Yeah.
50's up here. Which one do we replace it with? 50's here. Which one do we replace it with?
7.
Okay, 50 goes here. What do we do? We're done, right? Yeah, we're done. So you don't need to do anything more once you're at the maximum there. Okay, so that's it for remove for remove min. Okay, kind of neat, right? What is the asymptotic complexity of that? Yeah, it's pretty much logarithmic. One of the issues is this one's going to be a pretty big node. It's always going to be a pretty big node. So you're going to have to generally bubble down a little farther than you bubbled up before, just in general. But it's logarithmic, pretty good. Logarithmic is good. Okay, good. All right, here's how it works in this one. If we're removing min, 5 goes away. I'm just reiterating this. 5 goes away. 13 goes up there to where 5 is. Swap down, we're done. Okay. Big O we said was logarithmic. Okay. You can certainly practice it on, I got to pay the rent. Actually, I switched departments, so I don't even know what my rent is right now, but I guess I'll have to find that out. Okay. What's that?
It's a big surprise.
It'll be a surprise. This is a roommate I've lived with like 5 times in my life. And he owns the house, so he's cool. We'll see. All right. Okay. Remove smallest. Right. Remove smallest on here will remove in this case, the 1. Right. It removes the 1, and it's going to replace it with what? 14, and then it's going to replace the 14 with what? This is a 5 in this case, actually. So it's going to be 5, and then the 14 is going to be here, and then what? It's going to be the 8 here, and then back up there. So it's going to end up back up there. All right, let's see what that works. Remove smallest. That one's gone. 14, swap. 14, swap, like that. Okay, and we have a heap again. Woohoo! Right. All right. Now, a couple last things on heaps. What is the best method for building a heap from scratch? Try to think about that for a couple minutes. It's the last one I'm going to make you do today. Think about how to build a heap from scratch. There's an easy way, and there's a better way.
Are you talking about like with those numbers?
Turn those numbers into a heap, in other words. It's pretend it's an array. That's fine. Yep, you can pretend it's an array, or you can pretend you just get fed those numbers one after the other. That's a better way of thinking about it. Pretend you just get fed those numbers one after the other. Sure. What are you guys thinking? Okay, so 14 comes in first. What can you do? Insert, okay, and then what? Then 9 comes in. Compare, right? That would be kind of like just inserting, right? Can't you do insert, 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 and make the whole thing? Sure, you could. That turns out to be not the best method. That's okay. John, what do you think?
That's what I was thinking.
Just insert, insert. That works fine. That would work fine to build the heap. There's a slightly better way, which I wouldn't necessarily think of you guys figuring out, but you never know. You never know. Good. Got it? What's your idea? Well, we know that. What do you think?
We're thinking the like easy but probably really bad way would be to like take that as an input array almost, and then run like find minimum on it over and over and over again and create a new array where you put in. That would be really crappy. Or you could just take.
How could you run find min on it if it's not? Oh, you mean like in an array find min?
Yeah.
Yeah, that wouldn't be so great. Okay. What was your idea?
The actual one, that Erica thought was to just start with it as start with that as your array, and then just start reorganizing it, basically, right?
Yeah.
With the end and
Okay.
then divide by 2 and find its parent. And if it's less than its parent, you switch. And
I like that. That's actually a really good way. In fact, you're this close to the actual answer. This close. Okay, this is a tricky one. I heard a couple good responses. Got one that's really close. Okay, what's the easy way, first of all? What is it? Just insert them all, right? Start with 14, insert it into the heap. Then do 9, insert it into the heap, right? And you might have to do a couple swaps and whatever, but that's it. And then do the same thing okay. How long would that take? Well, it would be n to go through them all, and then what would we say the inserts for each insert was? Constant. Yeah, you're right, but you're right. It's kind of constant, so it's kind of like it's linear, but it's a linear plus, right? But you've got basically it's more or less logarithmic because the worst case is logarithmic for each insert, right? So that's you could do it that way. There's actually a slightly better way, which I never would have thought of on my own. Okay. Let's see. In this case, we're saying it's going to be kind of n log n. If you have it provably insert being better than that, then it's not quite that bad. But there's a better way. Watch this. Insert all elements into the tree in the original order. In other words, pretend it's just an array. Have it as an array and just throw them all in the original order. Right? This next line, you'll go, what are you talking about? Start from the lowest completely filled level. Oh my gosh, how do we find that? At the first node with children, right? That happens to be heap size divided by 2. That is the child, or the first element that has children. Or I should say the lowest completely filled level with a child. As it turns out, I'll show you in a sec. And then just down heap each element and back up on the tree until you get to the root. Okay? It's kind of cool. Watch how it works. Okay? All right. Here's your array. We insert it as if it's an array. Now we start at 1 because that's where we're going to start it, like always, right? And then start with the lowest level that has the element with the first element that has children. Doesn't it have to be 1, 2, 3, 4, 5, 6, 7, 8, 9? What's the 9 divided by 2? Is 4. 1, 2, 3, 4 is the first one that has children. Now this is exactly what you were thinking, except you kind of went a little bit backwards on it. You said start with last one divided by 2, which is exactly the same thing, right? So you're gonna go to this one and you're gonna say, fine, down heap this. What's it gonna do? Swap with 12, right? Because it's gonna swap with its smallest parent, right? Okay, and then you back up and you go to this one. Down heap it. What's it gonna do? It's gonna go to 8, right? And swap, and it's gonna be 8. And then that's it. And then this one. This ended up being 12. Are you gonna need to do anything with this one? No. And then this one. This one was 8 now, so I'll show you it again. It's gonna be down heap, like that. Whoa. You only have to do half the number that you thought of. Yeah?
What if there was like 11 in there? If there were 2 more?
If there were 2 more?
Yeah.
Okay. 11 divided by 2 is? 5. That's this one. Isn't that the first one with children? It would be if that was I should say the last one with children, I guess. But it's going to be this one that's going to be the first one going back up the tree, the heap that's got children. So it's going to be this one because it's 11 divided by 2. Just as if it was 10 divided by 2, same thing. Yeah. Okay. Let's walk through it. I'll walk you through this one. So you start out at I equals 4, which is the heap size divided by 2. Start there. Down heap it. 12 and 43 swap. Okay? And then you're now at I equals 3, meaning you're at the 13. Down heap it. 13 and 8 swap. Now you're at I equals 2. This is just a for loop, right? It's pretty easy. Don't have to do anything because 9 is smaller than both of its children. And then you're at I equals 1. Down heap the 14, which needs to down heap twice. Right? And then you're done. Nice. Right? Oops. Asymptotic complexity on this one is actually slightly better because you kind of cancel out half the tree immediately. Right? You start at this one, which is half of the elements already gone. So that's kind of nice. Okay? It's a little bit better way of creating it. And in fact, I believe that website actually has, build heap. It does it with random ones here. Actually, let me restart this. It's going to do it with random ones and show you how it's done. Let's see. Let's make the animation speed nice and fast so we know we can watch it. Just watch it for now. Build heap. Boom, 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 right? And it's basically going through the whole thing. It had to start with this one because this was the farthest one in the tree. But if you watch it slower, it's doing the exact same thing. Okay? And it's better than inserting. David.
So how does that actually affect the asymptotic complexity? Seems like it would still be linear. Half as many operations.
It's half the, it's better than, it's probably the same overall asymptotic complexity. It's just a better constant as far as going, like you only have to do half the number to begin with. So that's better in that sense. And you don't end up having to bubble everything up, right? Only half the things really get bubbled, as it turns out. Okay, good. Okay, so, boy, I got to start making lectures longer for this class. The other class finished right on time. You guys are 10 minutes early. Should I let you go early? Yes. All right, questions on this stuff? Okay, again, homework 5 will be out, I think, Wednesday when we start talking about sorting. Heaps, you'll get tested on, or you'll get practice on heaps next lab. And then tonight's lab is on tries. Okay, I'll see you guys later.